So welcome back, folks. So welcome to the second week of TM School 2016. I hope you had a good break from your first week of your TM School. And in this week, we'll be hearing some advanced topics in electron microscopy. The first one will be this convergent beam electron diffraction. And the first slide here, I have shown you guys some electron diffraction patterns. Specifically, apart from this pattern, 1, 2, 3, 4. These are some of the forms of convergent beam electron diffraction. And if you compare, these two patterns were taken in the same orientation. It's a 111 silicon. And here, as we use the parallel electron beam, we get the spot diffraction pattern. But as we use the convergent beam here, we have a disks. The spots are replaced with a disk and with a lot of information. And we can use all this information for different purposes. And in this lecture, we'll be hearing more how to quantify or how to use this sort of information and use for application for nanomaterials. So starting with a brief history, in 1931, as you guys know, the first TM was constructed by Max Knoll and Ernst Ruska. And in 1938, as soon as the TM was invented, the first technique to be used in the machine was CBED, that's convergent beam electron diffraction. And in 1947, due to some problems that were facing as soon as this technique was started to use, in 1947, the Jean Laue has invented selected area diffraction. So as soon as, the CBD is the first technique, primary technique, as soon as we get the TM. But comparatively, it's not really very famous enough as selected area, because most of you guys here, or if you have worked with the TM, you would have heard about selected area diffraction, but I believe none of you guys would have tried to do this CBD. The reason is, first, as soon as this CBD was invented, there was two problems. One is the contamination that was created by this focused electron beam, and there was specimen heating of the CBD. Means as we put a lot of spot or a lot of beam current onto the sample, the specimen is heating. Due to those two reasons, in 1947, the selected area diffraction was invented. But after a few days, by constructing a better and cleaner vacuum systems, the contamination problem was limited. And also by using a liquid nitrogen cooling holders, the specimen heat also was eliminated. Once after eliminating these two main problems with the CBD, the CBD should overtake the selected area diffraction, but it never happened. The reason was, until 1970s, no proper CBD patterns were produced. And as once mentioned by Professor Alvin Eads, who is a really very well-known expert in CBD field, he mentioned that the world was full of people who knew how to use selected area diffraction, and almost no one who knew how to use CBD. So those who thought microscopists continues to teach selected area diffraction, and it is what they knew. Maybe due to this historical collision, the selected area became really very popular compared to CBD. But I believe maybe after finishing this lecture, after realizing the potential of this CBD technique, you'll start using the CBD technique as your major primary diffraction-based technique in transmission electron microscope. So, as I said in the beginning, when we start with a parallel incident beam, illuminate the sample, thin sample, we get spot diffraction patterns. And when we replace this parallel incident beam with a convergent incident beam with a convergence of angle of alpha, the spots are replaced with the disks, and and those disks are separated by a Bragg angle. So here, one particular CBD disk can be considered as a rays coming from several selected area diffraction spots. So CBD, in general, CBD patterns can be considered as intensity maps of various scattered beams with respect to all incident beam directions. Next, before starting this, my plan was to give you some brief basics that are related to the CBD technique, and I will be discussing various applications of this CBD technique. When depending upon the application, I'll be giving you more basics. So in the start, I'll give you really very general basics, maybe a couple of slides, and then I go ahead with the application related points, and if that application requires any basics, I'll be giving you during that time. So the first primary parameter is deviation parameter, and this parameter can also be called as excitation error. And here the vector k naught is a transmitted wave vector and k is a diffracted wave vector. And in case of this XRD or neutron diffraction, as I think I mentioned about this point when I was showing you the demo session of CBED, if you want to get a diffraction pattern when you're using neutrons or X-rays, this evol sphere should lie exactly on the reciprocal lattice for viewing the peak. But as this electron beam has got a really very small wavelength, it's 0.00251 nanometer, it doesn't mean that evol sphere, even though if it is a little bit off from the reciprocal lattice, we are able to see some intensity. So here, when we consider this spot diffraction pattern, we have this transmitter, and here its evol sphere is a little bit away from the reciprocal lattice, so still we are able to see some intensity. And when you come to the CBED mode, the deviation parameter comes really very important parameter, and when you're dealing with dynamical or kinematical deviation, this parameter plays an important role. So understanding this is really very important. And the length of this reciprocal rod, it mainly depends upon the thickness, that's the extinction distance of your sample. And what exactly this deviation parameter signifies is how much amount the misalignment of a lattice plane with respect to exact back condition. And this one is really very important if you're tilting or if you're establishing a tubing condition or something like that. The deviation parameter based upon how much is the deviator, if you need to exactly illuminate the sample in such a way that there is a good, such as S is greater than 0 and S is less than 0, and we have the Kikuchi lines exactly in the center. Next, the next important point is here HOLZ reflection. HOLZ, and I believe I have shown you this picture earlier, but I have shown you a two-dimensional view of this picture. But in general, for understanding this HOLZ phenomena, it needs to be understood as a 3D sphere, because this HOLZ is a three-dimensional view. And if you view here, it's a circle when you're dealing with the zones, we are dealing a very base. And when you're working with the first order, that's a first order level zone, it's a little bit higher in the sphere, and the second order will be much higher than the first order. And the region inside the disk, when you're having a low camera length diffraction pattern, we have here, this region is called as zero order level zone. And this order, the details from here, we get only two-dimensional information. And if you go apart from here, this region, this is first order level zone and second order level zone. And these two are called as HOLZ information. And from here, we get the three-dimensional information. The reason is we need to understand the evol sphere as a sphere in a three-dimensional view. So here, from these two layers, we get a three-dimensional information. And the lines, and also I need to specifically indicate that what are HOLZ lines and HOLZ region. HOLZ lines are the lines that we see inside the zero order level zone. So we can see the HOLZ lines here, but those HOLZ lines carry three-dimensional information of a crystal lattice. And HOLZ region, the HOLZ region is the region away from the zones. So something like from here and here. Apart from this circle, the zero order level zone, these regions are called as HOLZ region. So there is a distinction between the HOLZ region and HOLZ lines. So we normally deal with both the parameters for understanding different applications. Next important part, what I want to mention is CLC, that's a center of level circle. So when you're working in the TEM, due to some misalignment, or if you want to establish a diffraction contrast imaging for whatever the reason, the incident beam always can be really very parallel to the optic axis. There may be a little bit tilt. In that cases, if there is a tilt, normally if this is an ideal case, and if there is any tilt, the CBED disks also will be moved, and that indicates if you consider any the disks just the disk will be moving, but the lattice, the information, these fine holes, these lines are called HOLZ lines. As these are related to the crystal lattice, they won't be moving. So if there is anything wrong with the CLC, just the disk will be moving, but not with the HOLZ lines, because the HOLZ lines are related to the crystal lattice directly. They don't move with if there is something wrong with the CLC. Next, as you know, this Kikuchi lines or HOLZ lines, I try to combine both of them in one slide, and I want to explain very briefly. And for the main criteria for seeing these HOLZ lines or Kikuchi lines, the specimen needs to be thick. The reason is simple. If the sample is very thin, it can't accommodate the multiple diffractions in it. So the sample needs to be really thick for accommodating the multiple scattering, and we can, as a result, we'll be able to see the HOLZ lines or Kikuchi lines. And these Kikuchi lines can be seen, or even the HOLZ lines can be seen in parallel incident beam or convergent incident beam. But when we see the Kikuchi lines in a parallel incident beam, the intensity is very low. Because it has the scattering in the parallel incident beam is because of inelastic scattering and elastic scattering. However, in convergent beam, we see the HOLZ lines or Kikuchi lines. The intensity is much better because most of the scattering in CBD mode is elastic in nature. And one more important point is causal cones. Once after finishing this kind of interaction inside the sample, the multiple scattering, they forms a causal cone inside the sample, and as they intersect with the backfocal plane of your TM, we get a straight lines. They are called as HOLZ lines, and mostly the difference between the Kikuchi lines is a kind of effect from zero at the level zone region, and HOLZ lines, it's a kind of locus of Bragg condition of HOLZ regions. So the similarities of HOLZ lines and Kikuchi lines, they appear in pairs. One is called as deficient HOLZ lines, and the other one is called excess HOLZ lines. Similarly, Kikuchi lines also, there are two types. One is called deficiency HOLZ lines, deficiency Kikuchi lines. Another one is the excess Kikuchi line. And deficiency lines are always dark in nature, which appear in the central band, if you consider the HOLZ lines of the CBD pattern. And the excess lines, they appear in a bright color, and they appear away from the central disk of the CBD pattern. Next, just I summarized what are the important basic points. The samples that we consider in a TM analysis are thin samples. So it does consist of incident beams, diffracted rays, and also, in addition to both of them, there is undeviated transmitted rays. And when you consider this, as I said in the first slide, the convergent beam electron diffraction has different orientations, and all these different orientations beams satisfy the Bragg's law simultaneously for producing the CBD patterns. And the causal cones, which are called as the geometrical locus of transmitted rays, forming cone with vertex angle pi/2 minus theta b, that is the Bragg angle. And the Kikuchi lines, it does have inelastic phenomena, but HOLZ lines, were purely elastic, so they are used for understanding the crystal lattice distortions. So next, the first primary application, and it's a really basic application, is understanding the thickness of your sample using CBD. From Hole-Wheelan equation, it is possible to understand the intensity of a diffracted beam, and by rearranging that Hole-Wheelan equation in terms of deviation parameter and extinction distance and thickness, it represents a form of straight line equation. And if you know the extinction distance of your sample, by just inputting into this sample into this equation, it straight away we can get the thickness. Of course, the deviation parameter is directly dependent upon the delta theta, which is dependent upon the spacing of these lattice fringes. And normally the thickness analysis is done in two beam condition because it's much simpler. If you go for a zone axis orientation, involving all the beams into the calculation is much harder. So to make things much simpler, we tilt away from the major zone axis and go for two beams. One is transmitted, one diffracted beam, and we, based upon this spacing, we understand the thickness. And as this equation represents a straight line equation, we plot this equation for different n values, And here I believe n is equal to 2, it's 0.999. It's really very straight linearity. It's showing really very linear enough. So and in this situation, based upon this value, we can get the, based upon the slope of the, we can get the extinction distance, and based upon the y-intercept of this line, we get the thickness. And doing the thickness analysis using this technique is very accurate enough, and the errors are only less than 2%. So next basic application of CBED is understanding the voltage determination. And in case of a small angles, this Bragg's law can be summarized, can be written as 2d theta b approximately equal to lambda, that's the wavelength of electron beam. And if you differentiate this equation with respect to lambda and theta b, or we get this form, that is change in Bragg angle is directly equal or dependent upon the change in accelerating voltage. Or if you differentiate this equation with respect to the lattice spacing with these two parameters, we can write this equation as something like this. So what these two equations represent? If there is any change in Bragg's angle, it influences the both accelerating voltage, or it influences the lattice parameter. That is, as these whole lines are directly related to the crystal lattice, if there is any change in Bragg angle, these lines are deviated with, as these are related formed based on the Bragg angle. And if there is any change in accelerating voltage or change in lattice distortion, these lines tend to move. So when you are working on a strain analysis, the first thing what you need to do is you need to calibrate your TM voltage. When the button says 200 kV, all the time it won't be exactly at 200 kV. There will be about 1K or 2K plus or minus depending upon the stability in your high tension of your TM. So and doing how to calibrate is really simple. We can use the two ways. One, by changing slowly the accelerating voltage by 1 kV and get a different CBD patterns and measure the distances between the holes in the intersections. So if we consider this line as one line and other one is the distance between this one and this one, the intersection points, they change, and based upon the distances change, we can estimate we can calibrate the accelerating voltage. Or because that way is not really very reliable, because if you change the accelerating voltage of a TM, it takes some time for you to wait until the accelerating voltage gets stabilized in the microscope. So the best way is just go onto the strain-free region of your silicon substrate and get a pattern like this, and in the modeling, something like a GEM software or something like that, just simulate for different accelerating voltages starting from 199 or 200, 201, 202 or something like that, and plot measure the distances between the intersections and see how the distances are varying over the range. Here I have tried to plot from 201 to 202.5, and here and in this distance I am trying to plotting the distances L1, L2, L3, that's the intersection point from here to here, how it is varying, and try to measure these values in your experimental pattern and try to input into this and calibrate your accelerating voltage. I believe this is the best method, and whenever you do the strain analysis, you need to do this one first and before going for looking into the more strain details. And also advantage is, one more advantage is, once after finishing this accelerating voltage calibration, we can also calibrate the beam convergence. Of course, we can measure the beam convergence, but using the modeling software, we can calibrate the beam convergence and the camera length as well. And using this technique, we can calibrate to the 0.04 kV. It's really very good. Next, so now after seeing some basics and some basic applications, the plan of today's talk is I want to implement CBD technique for understanding the etching effect, and then crystal polarity and crystal symmetry and crystal lattice range. These are the 4 applications I'll be covering in this today's talk. And I have arranged these applications in the kind of increasing complexing order. So starting with a minor one, it's an etching effect, it's a qualitative analysis. So I will just mention why it's a qualitative and why we can't do any quantitative analysis for this particular effect. And further next, I go for different applications. And I use the different samples because I can't do all the analysis on one particular sample. So I use the different samples for different applications. And here, the etching effect. And for etching effect, I used two different types of samples. That's a porous silicon and the silicon nanowires. And for both the cases, I'll be discussing why it can be quantitative analysis. So first, the porous silicon. Here, again, I have two different types of porous silicon. One is bulk silicon, which is unetched sample. And the other one is etched sample. It's after undergoing some etching process. So here, I try to use convergent beam imaging. I believe I have shown you guys in the demo session how to do the CBIM technique. And, but I haven't shown you how it can be very useful if you're dealing with the nanoparticles. This is the one I was telling you. Here is a nanoparticle, and when I get a CBIM imaging graph, I can straight away say that this area is not good enough, and this area is really good enough, because here the contrast is really very dark. So I can't do any good analysis, but here I can, just by seeing the image, I can say that, okay, this is my good region, this is the place where I need to, because I can see the HOLZ information here. So if I want to do any CBD analysis, this is a good region for doing it. And this is a secondary electron imaging. And here, these are secondary electron images that were acquired in TM, not in SEM. So due to that, there is a good contrast, and the resolution is much improved, as we have acquired these secondary electron images in TEM, not in SEM. And next, again, this is a SEM image of a etched particle, and we can see it's a topography of the surface. It's highly porous in nature. Now, starting with here, I can see there is some kind of fringes. So I believe they are thickness fringes. So first, I start to do the analysis in that particular bit here. And so this is my secondary electron imaging. I operated the machine in a scanning TM mode, and I acquired the CBD patterns. And it's much simpler because operating the CBD mode, obtaining the CBD patterns in STM mode, because I have a better control of the probe in STM mode compared to TM mode. So I have operated the machine in scanning TM mode, and I draw a spectrum imaging, and I acquired the series of images on that along that line. I can see that there is no shift in the HOLZ line positions, even though I acquired from the starting to down. That indicates there is no lattice distortion in this bulk sample. And this is the magnified, zoomed one. You can see here there is no distortion here. Next, here, this is my second one. It's a 100% etched sample, and I try to acquire the CBD patterns along one particular pore. And I believe this one will be working, but okay, that's good, it's working. Along this line, I had taken the several CBD patterns, and this is just I prepared a movie file based upon all the CBD patterns collected along this line. And we can, if you carefully look into here we see some kind of distortion here, movement of the HOLZ line positions here. But in case if you can't see that, no worries. Here, sorry. This is a zoomed version. You can see here, these are the two random patterns that were acquired from this series. And here the lines were above, and here the lines are below. So there is a kind of movement or shift in the HOLZ line positions. This indicates in the 100% etched sample, there is some kind of lattice distortions. So for understanding that lattice distortion, I correlated this technique with some other techniques such as diffraction contrast imaging. And I have acquired dark field images in 220 for bulk sample and 100% etched sample. Here we can see it's a kind of bright spots, and these are, but we can't see any pores of the surface, because this is not taken in secondary electron imaging mode. This is taken in a dark field image. So we have a plain view of the sample, and we can't get any topographical information from dark field imaging. And these are nanocrystallites, and due to the, from the before image, we can see due to the placement of these nanocrystallites inside these pores, that's causing a shift or lattice distortion in the crystal. So, but I can't quantify the shift of these HOLZ lines, because I don't know what is the quantity of these nanocrystallites. So I can't do any quantitative analysis here. So next sample is silicon nanowires. These are metal-assisted chemical etch sample, and I can see once after undergoing the etching process, it forms a rough edges on the sides, and I need to check whether even after finishing this etching process is still maintaining that this particular nanowire is still maintaining its crystallinity, or is there any phase or phase changes or strain stresses or exist at these rough edges. And of course, if I can do high resolution imaging and get the thickness fringes, and I can see if there is any change in the crystal lattice. But high resolution imaging is not good if the sample thickness is really very thick enough. And I believe this is really thick because I can see the CBD patterns. I can get a CBD patterns from these crystals, from these nanowires. So in these cases, high resolution team is not very useful. So I acquired again the secondary electron imaging in TM mode, and I acquired a series of CBD patterns, and I can see there is no shift in the CBD patterns. This clearly indicates that there is no changes or no stresses are present at the edges of the silicon nanowire. So it's a really very straightforward, but again, if there is any shift also, I can't do the quantification of this shift because I don't know what is causing this shift, or I don't know exactly what, if there is any crystallites are present in this sample also, I don't know. So it's a bit hard to do the quantification on this sample as well. So next application is crystal lattice polarity analysis. For this, I try to use cadmium sulfide nanostructures, and here these are hydrothermally synthesized cadmium sulfide nanostructures, and from here this is the second SEM image, and from here we can see that there is a flat edge on bottom, and there is exhibit a pyramidal shapes on the tip, and we need to understand why there is a different growth in the top and bottom of the surface of these nanocrystals. And also from the TM image, we can see that these crystals form kind of branches. And straight away, as these crystals are made of cadmium sulfide, we know that it doesn't have it's non-centrosymmetric in nature. So the main reason, if you're working with the CBD, is the failure of Friedl's law. Friedl's law is the main basis for observing any dynamical diffraction in the CBD patterns. So what exactly the Friedl's law says is, in case of centrosymmetric crystals, the structure factor of HKL is equal to the structure factor of minus H minus K minus L, and possess an inversion symmetry. But in case of non-centrosymmetric crystals, such as cadmium sulfide, it may be violated due to the multiple scattering among the zones reflections. So here, by plotting the intensity plots of 002 beams, we can straight away, means these are simulated plots, and by straight away we can say that the intensity of 002 is different from here. Based upon that, we can straight away say that, okay, fine, now its multiple scattering is influencing in our sample. But I tried, before going to the experimental analysis, I tried to do it theoretically, and then I tried to do the experimental analysis. So for understanding this, I tried to calculate the intensity obtained from a CBD pattern using Howe-Whelan equation. And this is a Howe-Whelan equation. It's a change in amplitude or phase of a scattered wave, and it's related based upon the structure factor. And in case of, if we extend this equation for n-beam case, it may think like this, it possesses something like this. And I mentioned here the Friedl's law is, failure of Friedl's law is occurring due to the multiple scattering among Zoll's reflections. So I try to use the multiple scattering by kind of a simple concept called double diffraction. I considered a thickness of a sample, a particular thickness, and I break the sample into two parts, layer 1 and layer 2. Layer 1, two layers, and as the electron beam passes through these two layers, I imposed a double diffraction concept, and I try to theoretically determine the intensity of a diffracted beam. So And this is the beams. Okay, one more thing is, once the electron beams is imprinted on the sample, it gives different scattered beams at the end of a layer 1. And these layers at the end of the layer 1 beams acts as a incident beams for layer 2, and we get a different beams at the end of the layer 2. So at the end of the layer 1, these are the scattered beams, and for I included this double diffraction concept, and I put these beams as a incident beam for layer 2, and I try to obtain the exit wave of the layer 2, and I have given here, I have given only the end results, and if you want to have quick overview of the derivation of this equation, please refer this thesis. And we can, in an exact zone axis orientation, where the deviation parameter is same for two particular beams, I can summarize this equation in the variables as C and Z and amplitude AG. So, using those concepts, I try to implement in a good orientation zone axis, such as 110, 1100 zone axis, and here I considered H1, H2, H3, H4 beams as the scattered beams from layer 1, and G minus H1, G minus H2, G minus H3, G minus H4. They are the beams that I got at the end of the exit wave of layer 2, and I tried based on these parameters C, Z, AG. I tried to calculate the intensity of 002 and 00 minus 2, and here just by making once after finding the amplitude, I squared the amplitude for obtaining the intensity of 002 and 002 minus 2 beam, and straight away we can say that just after one scattering event, such as one diffraction event, the intensity is not same for both the beams. So here this structure factor of F002 and F00 minus 2 is same before the scattering event. Once after one double diffraction process, they are no longer equal in this Argand diagram. So this confirms that the intensity of 002 is not equal to 00 minus 2, and it supports the violation of Friedel's law. But there is some conflict. This is the graph I have shown you in the first slide of a polarity analysis. Here we see that 002 beam has a brighter contrast, and here we 002 minus 2 has darker contrast. But from my calculation, I got this as a reverse process. So this one is darker and this is brighter. The reasons may be, here I try to include only 4 beams for at the end of the layer 1, but in a zone axis, as I said, we can have more than 4 beams, and it can have any beams. And if I include all the beams and I calculate the intensity, maybe I can get something like this. And also I did this calculation for a thickness of 16 nanometers. So I considered the 16 nanometers as 2 layers, 8 nanometers of each layer, and I tried to calculate the intensity. And in the C direction, there is a lattice parameter is about 0.6 nanometers, and it can accumulate. I included only 2 scattering events, but it can accumulate easily up to 26 scattering events. So maybe if I do all the process for 26 events and include many electron beams, then I can get something like this. So next, coming to the experimental point of view, just it's understanding theoretically it's a little bit tricky, but experimental it's much simpler. Just tilt a sample to a particular zone axis, such as a C-axis direction, so such as 110, and get an electron diffraction pattern from the tip, and I acquire this is the experimental pattern, and I try to simulate the CBD patterns for different thicknesses, and I try to match them, and there is a very good match between this experimental and simulated results. And straight away I can say this tip is I can say that this tip is cadmium rich and the flat edge is sulfur rich. So it's much simple if you are dealing with experimental analysis, but if you want to understand theoretically, you need to do a lot of theoretical analysis, and it's a little bit complicated. So the next one is crystal symmetry. Here I will be understanding the point groups and space groups of any crystal. So before going into it, I need to give you some terminology that is really very important for understanding this crystal symmetry. So what exactly the crystal symmetry operation means? So it means manipulating an object which leaves it unchanged is generally considered as symmetry operation. And there are 8 symmetry elements. That's 5 point rotation symmetry elements, 2 inverse symmetry elements, and 1 reflection. So, and if you have noticed here, we don't have a 5. That's the 5-fold symmetry, because that the 5-fold symmetry can be applied from combination of other symmetry elements. So it's not there. And what is the space groups? What exactly space groups are? So number of possible different symmetries that a 3D crystal can have are called as space groups, and they are 230 in nature. And these space groups are built on based upon the combination of these 8-point symmetry elements plus 2 translation symmetry elements such as glide planes and screw axis. And you need to understand that when you're dealing with the diffraction experiments, it's a bit hard to distinguish between a screw axis from a 2-fold rotation and a glide plane from a mirror symmetry. In that situations, we use the forbidden reflections, and we try to understand whether the system has got a glide plane or screw axis. Next, just based upon the these point symmetry elements, all the symmetries based upon these 8-point symmetry elements are called as point groups, and they are in nature 32 in nature. And a combination of these 7 different crystal lattice systems such as trigonal, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and cubic plus 4 lattice centering gives rise to 14 different types of Bravais lattice. And for based upon this CBD experiments, we have combining the 3-dimensional CBD diffraction patterns symmetries that relates to 32 point groups are called diffraction groups, and they are in general 31 diffraction groups. And again, depending upon how you set up the CBD pattern or how you acquire the CBD images, it depends. It's called it gives you the projection diffraction symmetry, and the symmetry of zones excluding the HOLZ information is called projection diffraction symmetry, and they are in general 10 in nature. And by including the HOLZ information, we get the whole pattern symmetry, and by excluding just by looking at the symmetries in the central CBD disk, we get the bright field symmetry. So these are really important things just you need to understand when you're working with the symmetry analysis using CBD technique. And and most of the times it's really simple. Just you need to train your brain what you need to look for in your CBD patterns. Then the analysis is much simpler. Once if you are able to understand this symmetry elements in your CBD pattern, you can combine to, or you can check with the tables in the International Crystallography database, and you can extract what is your appropriate point group or space group of your sample. So understanding these symmetry elements is much critical. So because this is the basis, if you want to understand the lattice or space group or point group of your sample, you need to understand what is the symmetry present in your sample, and this is the most crucial step. So I try to show you how a symmetry element 1, 2, 3 exists, and here are the patterns that were. I try to simulate these are simulated patterns that were from the different various materials, and here the symmetry element 1 means there is no symmetry. If an element doesn't have, or if a pattern doesn't have any symmetry, it is generally represented by 1. And here there is no symmetry here, and this is a point. And when I say symmetry element 2 means if you rotate by 180 degrees, I get the same pattern here. Replace by 180 degrees, you get the same pattern. So this got a symmetry element 2. And here the symmetry element is 3. That is, I rotate by 120 degrees, I get the same pattern here. So that's why I given this the symmetry of this pattern is 3. And next, symmetry element 4 means I rotate by 90 degrees, I get the same pattern. And here, when I rotate by 60 degrees, I get the same pattern. So that's why I get the symmetry element as 6. And what exactly is a mirror means, if I draw a line from top to bottom, the left hand side is equal to the right hand side. So and then I can say there is a mirror in it. So next, after understanding the symmetry elements, it's much simpler. For simple means, it depends upon your the clarity of your CBD patterns. It's much simpler. Generally, the CBD symmetry analysis is done in 3 steps. First, you need to understand the Bravey lattice type, and that is generally is done from reciprocal lattice. And then next point is I need to understand the point from this information. It's simple to understand the point group, and this one we get it from the diffraction groups, 31 diffraction groups of the CBD patterns. And from here, combining these 2 informations, it is easy to extract the space group information of your sample. And as I said, when you're working with CBD, we need to do the analysis in different camera lens, different exposure, different convergence angles. So you need to vary the parameters and get different types of CBD patterns. And you need to identify the symmetry elements precisely. If you can't do the symmetry, if you can't identify the symmetry elements properly, then it's impossible to get this analysis done. And you need to have access to the different tables from the crystallography tables, International Crystallography Database. And here, for an example sake, I took this titanium oxide commonly called as a root tile, and I try to determine the space group of this material. And this is a pattern that I acquired from 001 orientation, and straight away I can see that there is no forbidden reflection case for this sample, because I can see all the spots, I can index all the spots. So we can straight away say that this got primitive lattice centering. So next step is, once after finishing that, I try to use these 2 tables that were acquired from the International Crystallography tables, or initially was published by Buxton. And here first I need to understand the whole pattern symmetry and the bright field symmetry. So whole pattern means including the holes, and the bright field pattern means including the holes lines in the bright field disk of your CBD pattern. And based on this, I try to append these 2 symmetry elements present in the CBD analysis. And of course, dark field, if your CBD pattern is good enough, we can extract the dark field imaging that is away from the 00 disk. We get the dark field imaging, and we see if it doesn't have any symmetry elements present in the dark field. But in general, if you can understand the symmetry elements present in bright field and whole pattern, it should be fine enough to go ahead. And based on that, we get the projection diffraction group, and from there I can link to the diffraction group here. And further, I use this information into this table, and here is the diffraction groups, 31 diffraction groups, and I link that one to the point groups, and I extract the point group analysis, point group of your sample. So let's go ahead. Here, this is a pattern, a CBD pattern that was taken in 001 orientation, and by looking at the whole pattern, not in the transmitted disk, I can see that it has got 4 mirrors, one here, 2, 1, 2, 3, 4. So I can straight away say that my whole pattern symmetry in this particular orientation 001 has got 4 mm symmetry. And here, and looking into this second table, the first one, this table, I can see that it's got 4 mm symmetry, and the whole pattern is a 4 mm symmetry. So the projection diffraction group can be this one, 4 mm 1R, and based on that I can link, I can have, these are the number of different possible diffraction groups that this crystal can have. That's 4 MR, MR, 4 mm, 4R, MMR, 4 mm, 1R. These are the 4 possible diffraction groups. Now I need to reduce the possible diffraction groups, and I need to eliminate all this one. It can be one among these 4. So I go for a different orientation, so something like this, and when I take an image something in 101 orientation, I can see that both the whole pattern, including the holes, all the disks, and just looking at the bright field disk, I can see that it has got 2 mm symmetry. So that is 1 mirror here, 1 mirror here, 1 mirror here, 1 mirror here. So if I draw a line here, the left hand side is equal to right hand side. If I draw a line here, the top of the image is equal to the bottom of the image. So I can see that it has got 2 mm symmetry, and here I can see again from the whole pattern here, I can see that there is a 1 mirror existing. Oh, sorry, this is the one, And based on this information, 2 mm, I can extract the diffraction group as 2 mm 1R. And in the low camera length image of a CBED pattern, I can get this as a one mirror. Of course, the contrast is not really good. And maybe if you have a digital micrograph, we can enhance the contrast, and you can see there is only one mirror in this image. And based on that, we have the possible diffraction groups as, we can limit the possible diffraction groups as this many. And including these two, and we can eliminate different, and we can come back, means we can come to conclusion that only one diffraction group can exist, that is 2R MMR. So from the first incidence, we have 4 possible diffraction groups, and from the second incidence, we have one particular diffraction group. So based upon those two, here we can have, from here I said this is a diffraction group and this is a point group, and going through here, I can have here and 4 mm 1R here. So based on this, I can have the point group as 4/mm. So in this way, just reducing the possible options of your diffraction group, and finally come to a particular point group that is for your sample. Next, once after finishing the point group, we need to go for a space group, and here it's from the 2 steps above, I have this information it's got a p-type lattice, and it's got a 4/mm point group, and based upon these 2 information, I can limit of 230 space groups, I can limit to 16 possible options that this particular crystal can have, and from in this 16, I need to extract one for one particular space group. How can I do this? I can do based upon the lines called GM lines, or Jonas-Modi lines, or dark lines, or dynamic exchange lines, or in literature they call many forms. And based upon these lines, I need to reduce my number of possible options in the space group, and extract one particular space group. And these are some of the characteristics of a GM lines, because you need to understand, or we need to observe a GM line, or you need to precisely identify a GM line in your CBD pattern. Then only it is possible for understanding the space group of your sample. And in general, these GM lines are generated kinematically forbidden reflections. If your diffraction pattern has got any kinematically forbidden reflections, such as if you are working on a silicon, it's a 0002 is a forbidden reflection in a silicon. There is a possibility to see a GM line in that reflection, and it occurs due to the dynamical scattering. And GM lines can be seen with when the crystal is accurately aligned along the zone axis direction and viewed along a principal axis of your principal axis is always 90 degrees in the straight. Okay, I'll show you what exactly I mean principal axis. And the presence of GM line infers that a line is, and always it presents in the alternative reflection. Again, I'll be showing you how exactly the GM line can have. And GM line should appear for all the thicknesses, and should appear for all the voltages, and become narrower if you increase the thickness. If you increase the thickness, the GM line becomes, the line of 0 intensity becomes much sharper. And GM lines occur in HOLZ lines region, and also HOLZ lines. However, the appearance of GM lines in HOLZ region indicate the presence of a glide plane straight away. So always, if there is a GM line, if you see a GM line in a pattern, we can straight away say that a screw axis or a glide plane is present in your sample. But if you see a GM line in a HOLZ region, you can straight away say that your sample has got a glide plane, because a screw axis doesn't produce a GM line in this HOLZ region. So next, this is these two here and here is called as a principal zone axis of any diffraction pattern, and GM lines occur only here or here. No, it can't occur in this direction or in this direction. So always you need to look for a GM lines in a principal zone axis, principal direction of your zone axis, and always it occurs in a alternative reflection. So something like we get a GM line here, and we don't have a GM line here. We get a GM line here. We don't have a GM line here. Next, we can have a GM line here. So if you want to see a line, GM line means it needs to be in alternative reflections. Next, if you're using the tables that were published by Tanaka, he has mentioned, or he has nomenclatured this GM lines as A2, A3, A2, A3, B2, B3. So A to B2 means these are mainly seen in the zones, and if your hole lines or GM lines B3 and A3 are formed because of the holes region in your sample. And how to identify A2 line means if the deviation, diffraction vector is in this direction, always the GM line is parallel to a diffraction vector. So the GM lines that are staying parallel to a diffraction vector are called A2 lines, and if the GM line is perpendicular to the diffraction vector, so if the diffraction vector is going in this direction, if the GM line is seen here, that's called B2 line. And same thing, but it's the opposite if you're looking at a holes region. If you're looking at a holes region and if the GM line is something like a perpendicular to a diffraction vector line in this direction, that's called A3, and parallel the GM line and it's in the diffraction vector in this direction, that's called B3 GM line. So here, by looking into this incidence beam, the deviation vector 100 is in this direction and the lines is parallel in direction, and here the deviation the diffraction vector is in this direction and the parallel to the GM line, this GM line is parallel to that diffraction vector. So this pattern has got A2 lines. Based on that information, we can limit the number of possible 16 space group possibilities to 4. That's number 127, 128, 135, 136, and this is the part of the table that was in the International Crystallography database, and just looking into that, we can limit. Means I have given just part of it, just for information's sake, and now we are limited with the 4 different space groups. Now we need to pick one among these 4, and I looked into 100 orientation, 101 orientation, and I can see that there is a A2 type GM line in 010 disk here, but the appearance is really very broad. The reason is it's taken from very thin region. So if you increase the thickness, the intensity of this zero intensity line will become much smaller, and it's easy to identify. And so this orientation has got A2 type GM line. So that limits again the 4 possible to 2. That is space group number 128 and 136. And here in the third incidence, that's 110 orientation, I can't see any GM line here. So you should be really careful when identifying a GM line. So it's a good idea to go for different thicknesses for testing whether that has got a GM line or not. And I don't have any GM lines here, so I can precisely say that the space group of this particular material is 136. Number 136, that's P42/MNM. So next, here the final topic is the crystal lattice strains, and here I try to understand the lattice strains, and and I try to use the silicon germanium SLS structure for understanding the lattice strains in the structure. This is the geometry of the SLS structure. So it's got a various superlattice structures. So these bands are made up of silicon and silicon germanium, and here we can see the zoomed version here. And the size of these bands is about 10 nanometers, and the distance between 2 superlattice structures is about 1000 nanometers. It's really, so we can consider this particular region as a substrate for this silicon germanium layer. And from the bright field image, we can see that straight away that there are no defects at the interface, so we can consider the growth as a pseudomorphic in nature. And also we can see the lattice strains because all the layers are elastically strained. There is no inelasticity in the layers. So as when we prepare a sample from this bulk sample, material, there will be a change in strain state, because we mechanically thin the sample on the either sides and we make it to the electron transparency and we put it into the CTM. By doing that, we change the strain state. So it's very important to understand when the sample, how the sample or what is the strain state in the bulk material. So here, I said as the thickness of this films, it's 10 nanometers, and which is less than the critical thickness. There is a coherent growth in the epitaxial system. And coming to the strains, how these layers are expanded or contracted, along 001, that's a growth direction, we can see that silicon germanium is compressed because silicon germanium has a bigger lattice parameter compared to silicon. It's compressed, and however, the silicon which is in between silicon germanium, that's expanded because it's got a smaller lattice. It needs to be expanded and matched to the above top of the silicon germanium lattice. So there's silicon lattice thin film is in tensile state, and along the parallel orientation. So something like in this direction, the only silicon germanium is compressed, but the silicon lattice is doesn't have any strains in the parallel orientation. However, as I said just a while ago, when you prepare a sample from this bulk material, we thin on the both sides and we make it to 100 nanometers, and further we put it into the dimple and make it on dimple and ion milling, and we make a TM sample. Once by doing that, the strain state can be changed, and the strain and the maximum strain relaxation can occur on the top and bottom of the surface, and at the interface, it can no longer have a tetragonal distortion. So, and next, first we need to understand which zone axis is good for doing the strain analysis using CBD technique, and always I can say that one of the defect of CBD technique is we can't do using a CBD the strain analysis in exact zone axis orientation. It needs to be tilted away from the zone axis, because in a low symmetry zone axis, low index zone axis, it has high dynamical effects. So we need to eliminate those dynamic effects by going away from the low symmetry zone axis. So something like this here, and I believe I have shown you how to do this LACBD technique. We raise the sample by certain height, and by doing that, we get this reciprocal lattice into the focus, and this band, that's the region, it's out of focus. But we can straight away see that which lines or how good is it, because here we can see if a particular host line that is oriented parallel to this is a silicon germanium superlattice structure, individual layer. As the line of the host line comes nearby parallel to this interface, it tends to split. In the same way here, as this line it's oriented parallel, if this is a silicon superlattice, as this line is coming nearby to the interface, it starts to split. However, if a particular line that is oriented perpendicular to the interface, so this is our superlattice. If a line is really oriented perpendicular, so this is a lattice. If a line is perpendicular oriented, so it just pass away onto the lattice, and there is no impact. So an ideal zone axis needs to have a combination of both parallel and perpendicular oriented host lines. Then it's very easy to do the strain analysis. So for doing that, we have for choosing a good zone axis, I had tried to do for different zone axes, such as starting from 670, 560, 450, so on. And I tilted the sample by this much. And I need to be careful when you're tilting a sample from the 011 zone axis. If I increase this tilt angle, I'm just changing the lateral resolution. So I need to be careful about that. And here, the 670 and 350, 120 doesn't have any lines that are oriented parallel to the 110 direction. So this zone axis doesn't have any perpendicular or parallel orientations to the interface. So I can straight away eliminate these combinations. But 560 and 340 seems to be really good zone axis for doing the strain analysis. But if you look into the intensity of these host lines here, this is the experimental pattern, this is a simulated pattern. If you see the intensity of these host lines, the intensity is much lower. So it's these are taken from strain-free region, and if you go to a strained region, the intensity becomes much bad. So the appearance must be really good, and the best way is so here we have the 340 zone axis host lines, and we can see the host lines intensity is really good. So we try to do the host lines strain analysis in this particular zone axis. So next, if we obviously every zone axis has got a dynamic nature, and we need to check how much the dynamic nature is affecting these host lines. So I try to simulate different the host line patterns for various thicknesses, and we can see with the change in host line in thickness change, the intensity is getting better for increase in thickness, but there is no shift due to the thickness. So this indicates, even though this 340 has got a dynamic content inside it, it doesn't influence the Holstein pattern. So this 340 seems to be an ideal candidate for doing the strain analysis. So next, we need to understand when you're doing the strain analysis, we need to understand the strains outside the SLS structure and inside the SLS structure. So first, we scan the electron beam in this STM mode, and we get the diffraction patterns outside the SLS structure. And here, again, these images were taken in STM mode, operating the machine in STM mode, and the CBD patterns were collected. And when the electron beam is at position A, which is really very far from the interface, the lines are really very good, and it's really very sharp. And when it moves to electron B, position B, the lines gets a little bit bigger. And when it comes to position C, the lines start splitting, and it becomes three lines. So you can see here 1, 2, 3 lines, and here these are the simulated patterns of these experimental patterns. And what is the reason for this splitting? The reason of this splitting, split Holsteins, could be due to three causes. That is, inhomogeneous strain fields that are caused by defects. But from our bright field image here, we can't find any defects at the interface. So we can eliminate that one, or it can be due to the precipitates, and we can't see any precipitates in this bright field image, or plane bending. So we can think that the splitting of Holsteins could be due to the lattice plane bending. So just by understanding, we consider that as our reason for this splitting, and we try to simulate the patterns. How we simulate the patterns? This is the way. When the electron beam is at position A, we get the sharp Holsteins, and when the electron beam is at position B, the bent lattice can be considered as two different surface layers, one on the top and one on the bottom, and each layer gives one set of Holsteins. And as the electron beam comes from the top to bottom, we get two sets of CBD patterns overlapped on each other. Similarly, when the electron beam is at position C, the bent lattice plane can be considered as three different layers, one top, one in the middle, one in the bottom, and these three different layers gives each set of Holstein patterns. And as the electron beam passes from all these three Holstein patterns overlap on each other, and we get a triplet kind of thing. So based on that, we try to calculate the bending angle of a lattice plane for different thicknesses, and we can see that this is the interface. If you consider as this is a 0 as an interface, about less than 50 nanometers from the interface, we can't see any CBD patterns because the bending is too big. The patterns get distorted. So you need to remember that we have assumed that the cause for this split Holsteins is due to the lattice plane bending. And later we will use the analytical models, and we will check whether our assumption is correct or not. So next, as we scan the electron beam inside the SLS structure, we are operating the machine in scanning TM mode, and we take electron CBD patterns at one at a center inside the SLS structure. And here, the phenomena is a little bit different. Earlier case, when we are scanning the electron beam outside the SLS structure, the Holsteins getting splitted. But here, there is a shift in the Holstein positions. And we'll try to, there is no splitting. Of course, there is the intensity of this Holsteins is a little bit broader, but still we can see clearly see the shift in the Holstein points. We will try to quantify this shift in the Holstein points, and we will try to extract the strain information in this SLS structure. So for understanding this shift, I try to use the Hoff transformation, because we need to identify the shift really very precisely, and if there is, as these patterns were acquired from unfiltered CBD patterns, there is a lot of noise in the patterns. So maybe if we use a Hoff transformation, it can be a little bit better for identifying a spot and determining the distance between the two intersection points. And what exactly Hoff space means? It's a line in the real space is considered as a spot in the Hoff space. And here, if this is a general image, and by transforming this particular image into a Hoff transformation, we get all these lines as a spots in the space. And now it's very easy to identify the determining the distance between two spots. And doing in such a way that in that way we can increase the final resolution of the analysis. And here I'm able to analyze for a 0.5 pixel and 0.35 degrees. So it's really very good if you're working around strain analysis in this using this Hopf transformation. So, and one more problem with this CBD is using one CBD whole sign pattern, it is possible to extract all the 6 lattice parameters, but the obtained lattice parameters can be unique. For supporting that, I try to simulate same whole sign patterns using different lattice parameters. And you can see the appearance of these whole signs is exactly same for all these 3 patterns, even though there is a change in the lattice parameters here that are used for simulating this one. So for eliminating this ambiguity, we can do with 2 different types. One is we can make some assumptions and reduce the number of lattice parameters of your crystal lattice, and or we can do the strain analysis in different zone axes. But I'm afraid to do this strain analysis in various zone axes, because if I tilt the sample to a different zone axis, I'm not sure whether I'll be in the same position or not. So I try to use a crystal lattice assumptions, and I reduce the number of lattice parameters from 6 to 3 or something like that. So, and these are the assumptions that I have used for reducing my 6 lattice parameters. First assumption is, as we know that there is no defects at silicon and silicon germanium interface. So I consider that the TM sample undergoes orthorhombic distortion. We know that when the silicon and silicon germanium is in bulk state, they undergo tetragonal distortion. But I considered one level above tetragonal distortion. That's they undergo orthorhombic distortion, and I fixed what are the parameters for the electron beam direction and thinning direction and in plane and growth parameters. I fixed as A, B, C respectively, and then I considered that there won't be any relaxation in this particular orientation, and there will be a strain changes only in B and C direction. So using these 3 assumptions, I transformed my unit cell, and using this, and further at the end I got as A is equal to B is equal to 0.38403 nanometers for, and C as 0.54309 for transformed silicon unit cell. Using this transformed unit cell, I try to do all the simulations using GEMS, and now it's easy for me to understand how to quantify the whole signs patterns. So here, this is a strain-free pattern. When there is no strain, it's something like this. If I put a strain in C direction, all the lines will be moving, but if you carefully look, the lines that are oriented in this direction doesn't move for C direction. But if you put a changes in the B direction, if you put if I change strain in B lattice parameter, I change parallel, the lines whole signs that are oriented parallel, that's fine. But these lines that are oriented perpendicular, these change only for the changes in B, but not for C. So based on this, I try to first, for my experimental pattern, I try to obtain the B lattice parameter, and then using that as my information, I put it into the next one, and using a bilinear interpolation method, I try to calculate the C lattice parameter. So next, this is a technique. This is the method how I did the calculation for all the experimental CBD patterns. And first, I try to eliminate the B lattice parameter from the perpendicular interface whole signs positions. Then I use that value and I put into the C lattice parameter, and I calculate the C. So in this way, I repeated for all the diffraction patterns that were taken inside the SLS structure. So once after that, I was based upon that, I was able to calculate the strain inside the SLS structure. This band 1 is a silicon germanium layer, and this band 2 is a silicon layer. And I can see that there is no strain in B110 direction, and there is a strain, compressive strain in silicon germanium, as it's got a bigger lattice, and a tensile strain in silicon lattice, tensile strain in the silicon lattice. And as I used the Hopf transformation, my accuracy level was really very good, and I was able to do it for 2 to 4 into 10 power minus 4 of a nanometer. So, and also I was able to do this analysis on an unfiltered CBD pattern as I used Hopf transformations. So now I did some assumptions such as for split Holz lines, I assume that the lattice plane bending is causing the split Holz lines, and for strain analysis I did some assumptions and I reduced the number of lattice parameters from 6 to 3, and I try to evaluate the lattice parameters. Now I need to validate whether my assumptions are correct or not. So I try to compare with first model that is called finite element modeling. I try here using that experimental parameters, I try to simulate the model, and from here I try to calculate the strains of my SLS structure. And first I try to compare the lattice plane bending, and this is the black line is the strain results that I obtained from finite element modeling, and the blue line here we got it from the experimental CBD analysis, and there is a really very good compromise between them. So this clearly shows that my assumption that is lattice plane bending is valid enough. Next, I try to compare the strains that were acquired inside the SLS structure, and this is the strain profile that I acquired from the inside the SLS structure from experimental CBD analysis, and this step analysis, that was the strain profile that I acquired from finite element modeling. And we can see the intensity is, the magnitude is same for both of them, but when using the CBD technique I got a kind of Gaussian curve inside the SLS, but I got a step function profile when I'm inside the finite element, using the finite element modeling. So what is the difference? For understanding that, I try to use a different model. This is the analytical model. This model is based upon Fourier series, also called as Fourier series method, and this one initially done by Timoshenko Goodyear method. And in that analytical model, it is easy to understand the strain profile along the x direction, and using this equation I try to calculate the strain profiles using the second model. And one more thing I want to include here in this model is the reason why I used is I suspect that the change in the shape of the step to the Gaussian curve is due to the non-convergence of the CBD pattern. What I mean is, when the electron beam is on the top of the surface, as it goes ahead into the sample, the converged beam gets diverged inside the sample, and if the sample is, the electron beam is focused exactly in the middle of the sample, again there is a kind of divergence going as it proceeds through the sample. So I try to use this, I try to get this information, I input it into this equation. I modified this equation by including this information, and I try to plot a profile for various lattice beam sizes. And you need to be careful that beam size here is I use a different notation here. Beam size means the size which is obtained after considering the convergence angle, and here by changing the beam sizes we can see that when there is a beam size is 0, we get a step function as we have seen earlier, but if we change the beam size, it's trying to make a Gaussian curve. So taking on to this, by comparing with the experimental profile of a beam size of 8 nanometers, I'm trying to acquire a good comparison between them. So the step function, the variation of this step function and the Gaussian curve is due to the non-convergence of a CBD pattern. So this indicates there is a good agreement between them, and also the beam size defines the spatial resolution of the CBD strain analysis that we are using it. So in a general conclusion, CBD remains as one of the most efficient ways for determining sample thickness, lattice parameters, crystal orientations, and crystal polarity. And with the availability of field emission guns and better vacuum systems, the TM is becoming a very good option for doing the nanometer sized electron probes in CBD mode and performing analysis with a very good high spatial resolution. And of course, quantitative analysis of CBD method requires a time consuming, it requires a computerized modeling, but it can act as an independent analysis technique, or it can act as a supporting tool for XRD or micro-Raman analysis. And finally, more importantly, learning CBD technique helps not only just one technique, but it can be it can make things very easy for understanding different diffraction based techniques such as precision electron diffraction or rotation electron diffraction. Thank you.